Have you ever watched a humanoid robot walking across a room and thought, wow, this thing is basically ready to replace humans? It can climb stairs, recover after being pushed, carry boxes, and sometimes even run or jump. Then someone gives it a t-shirt and asks it to fold the shirt neatly. Suddenly, the robot looks completely lost. It grabs the wrong corner, twists the fabric, drops part of the shirt, and somehow turns a simple piece of clothing into a small disaster. That seems strange because walking looks incredibly complicated. A robot has to balance a heavy body on two relatively small feet, coordinate dozens of joints, react to the ground, and avoid falling over. Folding clothes, on the other hand, is something most of us can do while talking, watching television, or thinking about something completely unrelated. So why can an advanced AI robot walk but still struggle to fold a shirt? The answer is that walking and folding clothes are two very different types of intelligence. Walking mainly happens in a world of relatively predictable physics. Folding clothes happens in a world of chaos. Let me explain what I mean. When engineers teach a robot to walk, they are working with a machine whose body is carefully designed and measured. They know the length of every leg segment, the weight of every component, the range of every joint, and the amount of force each motor can produce. The robot also has sensors that continuously tell it what is happening. It may have joint encoders that measure the angle of each joint, inertial sensors that detect acceleration and rotation, force sensors in its feet, and cameras that observe the environment. All of this information can be converted into numbers. The robot knows that its knee is bent by a certain number of degrees. It knows how much pressure is under its left foot. It knows whether its body is leaning forward or backward. Walking is difficult, but it is a structured difficulty. The robot has a clear goal: keep its center of mass under control, move one foot forward, transfer its weight, and avoid falling. Once researchers build a reasonably accurate model of the robot and the environment, they can simulate this process millions of times. A simulated robot can fall again and again without damaging a real machine. It can try different movements, receive a reward when it moves forward, receive a penalty when it falls, and gradually discover a walking strategy. This is one reason reinforcement learning has become so important in robotics. A robot can practice years of simulated walking in a much shorter period of real time. And once the robot learns a stable walking pattern, much of the movement becomes repetitive. One step is similar to the next step. The left and right legs alternate. The forces change, but they usually change in ways the control system can predict. Of course, real-world walking is still extremely hard. Uneven surfaces, loose gravel, stairs, unexpected obstacles, and human contact can all create problems. But compared with handling clothing, walking has one major advantage: the robot's own body is predictable. A shirt is not. A shirt has no fixed shape. Place the same shirt on a table 10 different times, and it can create 10 completely different shapes. One sleeve may be hidden underneath. The collar may be folded inward. The fabric may be wrinkled, stretched, twisted, or partially hanging off the table. The robot does not simply need to recognize, this is a shirt. It needs to understand the current three-dimensional configuration of that specific shirt. Where is the left sleeve? Where is the right sleeve? Which visible edge belongs to the front of the shirt? Is that corner actually a corner? Or is it a fold covering another section of fabric? For humans, these questions feel almost automatic. We look at a pile of clothing and immediately understand which parts belong together. But our brains are using a huge amount of experience. We have spent our entire lives touching soft objects. We understand that fabric bends, stretches, slides, wrinkles, and changes shape when pulled. We know that lifting one corner may cause the rest of the shirt to unfold. We do not consciously calculate these things. Our brain predicts them in the background. A robot has to somehow learn the same kind of physical intuition, and this is where the problem becomes much harder. In robotics, objects such as metal tools, plastic boxes, and machine parts are often called rigid objects. Their shape stays mostly the same when the robot touches them. If a robot sees a cup, the cup remains a cup-shaped object when the robot picks it up. The handle does not suddenly move to the other side. The bottom does not collapse. The entire object usually moves as one unit. Clothing belongs to a different category. It is a deformable object. When the robot grabs one part of a shirt, the rest of the shirt changes shape. Gravity pulls the fabric downward. Friction affects how it slides across the table. Different materials behave differently. A thick cotton sweatshirt does not behave like a thin silk shirt. A wet towel does not behave like a dry towel. A pair of jeans does not deform like a sock. Even two apparently identical t-shirts may behave differently because one is older, softer, or more stretched than the other. The robot is not just moving an object, It is changing the object while trying to understand it. That creates a loop. The robot looks at the shirt and estimates its shape. Then it touches the shirt. The touch changes the shape. Now the robot's previous estimate may no longer be correct, so it has to observe the shirt again. This is sometimes called the perception action loop. Humans perform this loop incredibly quickly. We look, touch, adjust, pull, and reposition, almost without noticing. A robot may need to stop, capture another image, calculate the new position of the fabric, plan a new movement, and then carefully try again. And vision alone is not enough. A camera can show the robot what the outside of the clothing looks like, but fabric often covers itself. Important parts may be completely hidden. Imagine that one sleeve is trapped underneath the body of a shirt. No camera placed above the table can directly see the hidden sleeve. A human can lift the shirt slightly, feel the resistance, and understand that something is underneath. That ability depends on touch. Human hands are filled with touch receptors. We can sense pressure, texture, slipping, stretching, temperature, and tiny changes in force. When I pick up the edge of a shirt, I can immediately feel whether I am holding one layer of fabric or several layers. Most robot grippers are nowhere near this level. Some advanced robotic hands include tactile sensors, but artificial touch is still much less detailed and less reliable than human touch. The robot may know that it is applying 5 newtons of force, but that does not necessarily tell it whether the cloth is about to slip, whether it has grabbed 2 layers, or whether a hidden fold is creating tension. Then there is the problem of the hand itself. Walking robots can use strong electric or hydraulic actuators, because legs are relatively large. A robotic hand has very limited space. Engineers need to fit motors, gears, sensors, cables, and control electronics into something roughly the size of a human hand. Human hands have more than 20 degrees of freedom, depending on how they are counted. Our fingers can move independently, coordinate with the thumb, and change grip strength in extremely subtle ways. We can pinch a thin piece of fabric with our fingertips, slide one finger underneath it, hold tension with the other hand, and change our grip without dropping the shirt. That is an incredible mechanical system. Many robots still use simple 2-finger grippers. These grippers are excellent for picking up boxes or machine components, but they are not ideal for separating 2 layers of cloth or finding the exact edge of a sleeve. A humanoid hand may look more like a human hand, but appearance does not automatically create human-level control. The robot still needs to decide exactly where every finger should go, how much force it should apply, and when it should release. Even a tiny mistake can ruin the fold. And there is another important difference between walking and folding clothes: the definition of success. For walking, success is relatively easy to measure. Did the robot move forward? Did it stay upright? How much energy did it use? How quickly did it reach the target? These goals can be expressed mathematically. But what does it mean to fold a shirt correctly? Should the sleeves be perfectly aligned? How much wrinkling is acceptable? Does the final rectangle need to match a specific size? Is a slightly uneven fold still successful? Humans can look at the result and say, that is good enough. Teaching a robot what good enough means is surprisingly complicated. This also makes training data harder to collect. We have huge amounts of video showing humans walking, but a walking controller can also be trained through simulation. Simulating cloth accurately is much more computationally expensive. A shirt may need to be represented by thousands of connected points. Each point interacts with nearby points, the table, the robot's fingers, gravity, friction, and collisions. Small errors in the simulation can produce very different results. A strategy that works perfectly with simulated fabric may fail immediately on a real shirt because the real material stretches or slides differently. This gap between simulation and reality is often called the sim-to-real gap. Researchers try to solve it by randomizing the simulation. They change friction, stiffness, weight, texture, and lighting, so the robot learns a strategy that works across many conditions instead of memorizing one perfect virtual shirt. But deformable objects create an enormous number of possible conditions. This is why household robotics has progressed more slowly than many people expected. A factory is designed for robots. Objects arrive in known positions, lighting is controlled, tools are standardized. The same action may be repeated thousands of times. A home is the opposite. Every room is different, every object can be moved. Clothes are mixed together. Children leave things on the floor. Pets walk through the workspace. Lighting changes throughout the day. For a robot, the home is not a simple environment. It is one of the most difficult environments imaginable. The interesting part is that folding clothes may actually be a better test of general intelligence than walking. Walking shows that a robot can control its body. Folding clothes shows whether the robot can see, touch, predict, adapt, and recover from mistakes in an uncertain world. A robot that can reliably take a random shirt from a laundry basket, unfold it, identify its orientation, remove wrinkles, fold it neatly, and place it in the correct drawer is solving many problems at the same time. It needs computer vision, tactile sensing, motion planning, force control, object understanding, long-term task planning, and common sense, and it has to combine all of them in real time. That is why you should not judge a robot only by its most dramatic demonstration. A robot performing a backflip looks more impressive than a robot slowly handling a towel. But the towel task may involve more uncertainty and more general intelligence. The backflip can be heavily planned, practiced, and controlled. The towel refuses to cooperate. Researchers are making progress. Robots are getting better tactile sensors, more flexible hands, stronger vision models, and AI systems that can learn from human demonstrations. Instead of programming every movement manually, engineers can show robots videos or record the movements of human operators. Large vision language models may also help robots connect visual information with instructions, such as find the sleeves and fold them toward the center. But we are still discovering that understanding language is not the same as understanding the physical world. An AI model may explain how to fold a shirt perfectly. That does not mean it can control two robotic hands well enough to do it. Knowledge and physical skill are connected, but they are not identical. Humans learn this through years of interaction. As children, we grab objects, drop them, pull them, tear them, squeeze them, and build an intuitive model of physics. Robots need their own version of that experience. They need to interact with thousands of objects, make mistakes, and gradually learn what different materials will do. So when you see a robot walking confidently, but struggling with laundry, it is not because engineers forgot to teach it a simple household task. It is because the physical world is far more complicated than it looks. Walking is a difficult control problem inside a relatively structured system. Folding clothes is an open-ended perception and manipulation problem involving an object that changes shape every time you touch it. To us, a shirt is ordinary. To a robot, it is a constantly changing puzzle with hidden pieces, uncertain physics, and no single perfect solution. And that is the real lesson here. The hardest tasks for robots are not always the tasks that look dangerous, athletic, or impressive. Sometimes, the hardest task is sitting quietly inside your laundry basket.